Hi, in this video, we're going to introduce another graph problem called the minimum spanning tree problem. So we have seen that graph can be used to represent things like a water distribution system when we talk about the max flow problem. So just as well, a graph can be used to represent something like an electrical grid. And in this graph or grid, basically the vertices are power plants, those that generates power, and then the houses or condos that we live in, and then the edges that connect the power plants to the residential units. Those are the electrical wires. Okay, so another very common problem in such a graph, let's say an electrical system or a water distribution system, is how to connect all these different endpoints, right? How to connect the power plants and all the houses using the minimum amount of wires, or in case of the water distribution system, how to use the minimum amount of pipes to connect all of these endpoints together. And it has the obvious benefit of, the least wire or the least pipes that we have to construct, the least money we have to spend on them, and also it's higher efficiency, right? Because we don't have to spread things out um, in a wider kind of a network. So this kind of problem is what's called a minimum spanning tree problem. So a little more formally, when we talk about minimum spanning trees or MST, we're talking about it in the context of a connected, edge-weighted, and undirected graph. So it connected means all the vertices are connected to each other. There's not a single vertex that is disconnected from the rest of the vertices. Edge-weighted just means each edge has a weight, just like all the graphs that we discussed previously. And all these edges, they do not have a direction, so they're undirected edges. Now, so the MST is a subset of the edges in this graph, and it connects all the vertices together, and it does not have any cycle. And then the total weights of all the edges in this subset of edges is the minimum possible. Okay, so for example, in this very simple graph that has 3 vertices and 3 edges, the subset of edges that forms the MST are these 2 edges. So the first thing is that these 2 edges, it spans all 3 vertices. So that's what spanning means, right? It connects all the vertices. And note that the MST does not include this edge of weight 4 because it just doesn't need it. These 2 edges is by themselves can already connect all 3 vertices. So it's enough for spanning. And then the second thing is that it must be minimum. So that means there's no other spanning tree whose total weight is lower than the MST, right? So obviously we can say we can have a different spanning tree in this graph that is, say, 2 and 4. So 2 and 4 would also connect A, B, and C, but it's not minimum because the total weight would be 6, which is higher than this minimum spanning tree, the total weight of which is 3. And finally, minimum spanning tree is a tree. It's not a minimum spanning graph, right? So the main difference between a tree and a graph is that tree is a graph that has no cycles. And so minimum spanning tree, it has to be a tree because if there's a cycle, so for example, this graph, if we pick all 3 edges, then it has a cycle. However, we can actually remove any one of these edges, and the remaining edges, it still can span all the vertices in the graph. And because we remove an edge, the resulting spanning tree / graph must be smaller than the one that has cycles in it. So that's why um, minimum spanning tree should never have cycles, because we can always remove an edge, break the cycle, and end up with a smaller spanning tree. All right, now that you've seen the definitions, so a small example. Now take a look at this graph here. So this is G. This is just the graph. It's slightly more complicated than the one that we just saw, with an additional edge here, and the weight here is actually 2 instead of 4. Now look at the rest of um, these trees or graphs here and see which one of them is a minimum spanning tree of G and which one is not. All right, so hopefully you've done that. Let's go through, excuse me, the answers together. So the first one, well, are these two edges, do they form the minimum spanning tree? Well, not quite, because these two edges, they do not connect the vertex A, so it's not spanning. Okay. What about this one? Is it the minimum spanning tree? Well, it is a spanning, and it's a tree because there's no cycle, but it's not the minimum. As we'll see, we can find a spanning tree that has smaller total weight. What about this one? Well, it is a spanning graph, but it's not a tree because there's a cycle, right? And because there's a cycle, this is definitely not minimum. Okay, so lastly, if we look at this one, well, this one would be a minimum spanning tree because you add up all the weights together is 6, compared to this one, all the weights add up to 7. So this is smaller, and as a matter of fact, this is the smallest you can get. Now, at the same time, this is also a minimum spanning tree because you add up all the weights is also 6. So a minimum spanning tree of a particular graph, it doesn't have to be unique. There could be multiple minimum spanning trees for a given graph. So why study minimum spanning trees? Well, as we said earlier, right from the beginning, that it's actually very useful in a lot of real world applications. As a matter of fact, the very first application of MST was to construct an efficient electricity network for a town in Czech Republic back in almost 100 years ago. So this has a long history. And that algorithm was invented by this mathematician whose name I shall not try to pronounce. Anyway, so it's useful, but not just in an electricity network, but in many other applications. And some of those are mentioned in your readings. And as far as the solution goes, there are multiple algorithms that can find the MST of a graph. So obviously, the first person who did this back in the early in the 20s, he's got his algorithm. There's an algorithm by Prim, and then there's an algorithm by Kruskal, and there are several others. So what we will study is we'll study Kruskal's algorithm, and it was published in the 50s by Joseph Kruskal.